Hello everyone. In this video, I will discuss about the how to find the stresses in composite bar due to the temperature change. So this is I will discuss with one example problem. Let's see the problem. A flat bar of aluminum alloy 30 mm wide and 8 mm thickness is placed between the two steel bar each of 30 mm wide and 10 mm thickness to form a composite bar of 30 mm into 28. This is the mm. So 28 mm as shown in the figure. So this is the figure. So the three bars are fastened together at their ends when the temperature is 12 degrees. Find the stresses in each of the material when the temperature of the whole assembly is raised to 42 degrees centigrade. If a new temperature, a compressive load of 30 kilonewtons is applied to the composite bar, what are the final stresses in the steel and aluminum? Here problem is given that aluminum bar, so this is the aluminum bar, is placed between the two steel bars and fastened together at their ends, which means, so this is become a composite bar. Here we have to find the stresses in two conditions. So first condition is find the stresses when the temperature rise. So this is the find the stresses when the temperature rise. And the second condition is at a new temperature applying the compressive load of 30 kilonewtons, then we have to find the final stresses in the each material. Here one more thing we have to observe, that one alpha value of the aluminum, which is 23 into 10 to the power minus 6 per degree centigrade, is greater than the alpha S, so which is the 12 into 10 to the power minus 6 per degree centigrade. So thermal expansion of the aluminum is greater than the thermal expansion of the steel. So which means, so delta AT, which means thermal expansion of the aluminum due to the temperature change, that is the delta AT, is greater than the delta ST, which means thermal expansion of the steel due to the temperature change. Why mean alpha A is greater than the alpha S. But due to the composite bar, thermal expansion in the aluminum is equal to the thermal expansion of the steel. Let us consider this is the final expansion. So in the both of the materials should be the equal. Why mean it is the composite bar. So individually means if you taken the individual, then thermal expansion of the aluminum should be greater than the thermal expansion of the steel. But when you considering the composite, the final expansion in the both of the materials should be the equal. So in the aluminum, contraction takes place due to the compressive stresses. So in the aluminum, compressive stresses it will be generated and contraction it will be takes place. Similarly, in the opposite behavior in the steel, tensile stresses it will be generated and the expansion it will be takes place. So here, so this is the delta S sigma mean expansion in the steel bar due to the tensile stresses. Similarly, delta A sigma means so contraction of the aluminum due to the compressive stresses. So here notations also once again I have to note down. Delta AT is, this is the delta AT. So free expansion of the aluminum due to the temperature rise, which is greater than the delta ST. And delta A sigma equal to the expansion of the aluminum due to the compressive stresses. So compression of the aluminum due to the temperature stresses, the nature is compressive. Similarly, delta ST equal to the free expansion of the steel due to the temperature rise. This is the delta ST up to here. And delta S sigma equal to the expansion of the steel due to the temperature stresses, the nature is the tensile. So expansion it will be takes place, that the expansion is delta S sigma. And once again I have to observe the given data. So in the given data is the, so we have to note down area, cross section area of the aluminum is given, that is the 8 mm thickness and the 30 mm wide. So it is the rectangular bar. So rectangular bar means So width into the thickness, that is 30 into 8, that is will become the 240 mm square. Similarly, cross section area of the steel also is given. So steel is having the 10 into 30. So 10 mm thickness and 30 mm the width, but it is consisting of the two steel balls. So that's why 2 into 10 into 30. So which will become the 600 mm square. And now, yeah. So next we have to applying the statics and the compactability condition and geometry conditions for the composite bars, which is the first condition is, so from the statics we know that when the tensile forces generated in the steel equal to the compressive forces generated in the aluminium, that is the PS equal to PA. Let us consider the value equal value P. So PS is nothing but tensile forces in the steel bar equal to the P of A is nothing but compressive forces in the aluminium bar, which is equal to, let us consider P. And second condition is, let us consider this is the equation 1. And the second condition is compactability equation. We know that when the final expansion in the aluminium and the final expansion in the steel, so both will be equal. Then let us consider delta A equal to the final expansion in the aluminium, which is equal to the final expansion in the steel, that is the delta S. Let us consider delta. Let us consider this is the equation number 2. And third one, from the geometry, just have to observe this geometry here. So this is the final expansion of the steel, so which is equal to the delta ST plus delta S sigma, which means expansion of the steel due to the temperature rise plus expansion of the steel due to the tensile stresses. So this is only we have to write down final expansion, that is the delta S equal to, so this is the final expansion. So delta S equal to delta ST plus delta S sigma. Similarly, final expansion of the aluminium we have to write down. So this is the final expansion in the aluminium, so which is equal to the delta AT minus delta A sigma, which means, so final free expansion, so expansion of the aluminium due to the temperature change, that is the delta AT minus delta A sigma, which means expansion contraction due to the compressive stresses. So this value. So let us consider this is the equation 3. So, and we know that when the final expansion, that is the delta S equal to the delta A, here we have to substitute this delta S and delta A values in this equation. We will get the delta ST plus delta S sigma equal to the delta AT minus delta S sigma. So this is once again we have to write down the delta A sigma plus delta S sigma equal to the delta AT minus delta ST. And we know that when the, so delta AT, which means thermal expansion of the aluminium due to the temperature change. We know that one the, that is the equal to the L alpha A into T. Similarly, delta ST, which is nothing but thermal expansion of the steel due to the temperature change. So that is also we know that one the L alpha delta, which is nothing but L alpha S delta is nothing but T, temperature change. So L alpha S T. So here we have to directly, here directly I wrote down. So LT is common, we have to take alpha A minus alpha S. So delta A plus delta S, so delta A of sigma plus delta S of sigma, which is equal to the LT into alpha A minus alpha S. So next we have to find the stresses in each material by temperature rise. The temperature rise is, the final temperature is 42 degrees centigrade and initial temperature is the 12 degrees centigrade. So temperature rises, so final temperature minus initial temperature, that is the 42 degrees centigrade. So for this one we are using the three condition. So in the previous slide we already discussed. The first one is from the statics. So forces, tensile forces in the steel equal to the compressive force in the aluminum bar, which is equal, that is, let us consider that is the P. Similarly, final expansion in the aluminum equal to the final expansion of the steel. So that is, let us consider delta. And also we know that when the final expansion of the steel equal to the, so here from see from the diagram, delta ST plus delta S sigma, which means expansion of the steel due to the temperature rise plus expansion of the steel due to the tensile forces. Similarly, delta A also had to write down. So delta A, this is the final expansion. So this is the final expansion. So this is, we have to write down the, so delta AT minus delta A sigma, which means, so thermal expansion of the aluminum due to the temperature change minus delta A sigma, which means expansion of the aluminum due to the compressive stresses. Sorry, contraction of the aluminum bar due to the compressive stresses. So let's go to the first one, that is the forces in the steel and aluminum equal. So we know that one, the force, we have to write down the stress into the cross sectional area. Similarly, forces in the steel bar, which is equal to the, so tensile stresses in the steel bar into cross sectional area of the steel equal to the compressive stresses in the aluminum bar into the cross sectional area of the aluminum bar. And we know that one, the cross sectional area of the steel equal to the 2 into 10 into 30, that is the 600, that is the 600, which is equal to the sigma A into cross sectional area of the aluminum. Aluminum, we know that one, the 8 into 30, that is the 240. So from this one we have to say that one, delta A equal to the 600 divided by 240, which is equal to the 2.5 sigma S. Next I have to go for the second equation, that is the final expansion in the aluminum and final expansion in the steel, both are the equal. And so substitute this delta S and the delta A in this equation. So I have to say that one, delta S of the T plus delta S of sigma equal to the delta of AT minus delta A of the sigma. So here we know that one, the delta S T, which is the thermal expansion in the steel bar, so equal to the L, so LT alpha S, and so this is the delta S sigma, which means expansion due to the tensile forces. So which means, so PS, so we know that one, PL by AE. So due to the expansion due to the stresses. Similarly here also have to write down the PS, tensile forces in the steel, into L divided by cross section area of the steel into the Young's modulus of the steel. So which is equal to the delta AT mean thermal expansion due to the temperature change. We know that one, that is the L alpha T. So which means LT alpha A aluminum minus, so this is the delta A sigma, which is nothing but expansion or maybe contraction due to the, so contraction due to the compressive forces. We know that one, contraction due to the stresses mean is nothing but PL by AE. Here also same thing, P of A, compressive force in the aluminum. So L, length of the aluminum bar, divided by cross section area of the aluminum into Young's modulus of the aluminum. So this is, once again we have to write down the LT alpha S plus, we know that when the force divided by the cross section area is nothing but, so stresses. So that is the sigma S for the steel, sigma S L divided by Young's modulus of the steel, which is equal to the LT alpha A minus, so this is the, so force, compressive force divided by the cross section area is nothing but sigma of the aluminum, so into L divided by EA. So in this equation take the L is the common, so here, so L is the common in right hand side and the left hand side, so it will be cancelled. Then equation will become the T alpha S plus sigma S by ES equal to the T alpha A minus sigma A by EA. So we know that when the T is the, so temperature change or temperature rise. So that is the T equal to the final temperature minus initial temperature. We know that the final temperature is 42 degrees centigrade and initial temperature is 12 degrees centigrade. So then the T will become the 30. Then we have to substitute the all the values in this equation. So here T equal to 30 and alpha s. Alpha s is given in the data, that is the 12 into 10 to the power of minus 6. Sigma s we don't know the value, so just we have to keep the sigma s divided by es, Young's modulus of the steel is given that one 2 into 10 to the power of 5. So equal to the t, that is the 30. Alpha e is given in the data, that is the 23 into 10 to the power of minus 6. Sigma a we don't know, so just we have to keep sigma a divided by ea is given that one 0.7 into 10 to the power of 5. So from the here, so we know that one the relationship between the sigma a and the sigma s, that is the sigma a equal to 2.5 into the sigma s. Just we have to substitute in this equation sigma a value as the sigma s, that is the 2.5 into sigma s. So here then you have to solve this equation. Just we have to send this one into this side. So it will become 2.5 sigma s divided by 0.7 10 to the power of 5 plus sigma s by 2 into 10 to the power of 5. So sigma s they have to take in common, and you have to solve this equation. Then finally you will get the answers are the sigma s equal to the 42 Newton per mm square. Then substitute sigma s value in the sigma a equation. Then we will get the sigma a value is the 105 Newton per mm square. We know that the nature of stresses in the steel bar is the tensile, and nature of stresses in the aluminum bar is the compressive. So next you have to find the stresses due to the applying compressive load of 30 kilonewtons at the final temperature. So this is like the composite bar applying the load, and we know that total load should be equal to the load on the aluminum bar plus load on the steel. And also we know that one load is nothing but stresses into the cross-sectional area. So here, so load on the aluminum bar, which is nothing but stresses in the aluminum bar plus cross-sectional area of the aluminum bar plus load on the steel bar, which is nothing but stresses on the steel bar plus cross-sectional area of the steel bar equal to the total applying load. So that is the 30 kilonewtons. So which is equal to the 30 into 10 to the power of 10 cube. So we know that when the cross-sectional area of the steel is 600, cross-sectional area of the aluminum is 240. Then you have to substitute AS and AA values in this equation. Then equation will become FS 600 plus FA 240 equal to 30,000. So then, and also we know that when the in composite bar, strain of the aluminum bar equal to the strain of the steel bar. So which is nothing but, so epsilon S equal to the epsilon A is nothing but, so we know that when the strain is nothing but stress divided by the Young's modulus. Similarly here, so strain of the steel bar, which is equal to the stress of the steel bar divided by Young's modulus of the steel bar, which is nothing but Fs by Es equal to the stresses in the aluminum bar divided by Young's modulus of the aluminum bar. So which is nothing but Fa by Ea. So we know that from the given data Es and Ea values, so just we have to substitute here. So from this equation, Fs is nothing but Es by Ea into Fa. So this is the Fa into Es by Ea. So Es equal to 2 into 10 to the power of 5. Ea equal to, sorry, here 0.7. 0.7 into 10 to the power of 5. So 10 to the power of 5, 10 to the power of 5 will cancel. Then 2 divided by 0.7 Fa. So which is equal to the 2.857 Fa. So Fs equal to the 2.857 Fa. And also this value, Fs value, Fs equal to the 2.857 Fa. This value you have to substitute in the fourth equation, that is the Fs 600 plus Fa into 240 equal to 30,000. Here we have to substitute the, so Fs value, then here, so Fs value equal to the 2.857 Fa into 600 plus Fa into 240, which is equal to the 30 into 10 cube. So then Fa have to take the comma, then you have to solve. We will get the value equal to the Fa is 15.4 Newton per mm square, and nature is here we are applying the compressive load. So obviously stresses is the compressive stresses. Similarly Fs value, which is equal to the, so 2.857 into the Fa, so that is the 15.4 into 2.857, then the value we will get the 43.9 Newton per mm square. the nature is here we are applying the compressive load, so obviously compressive stresses will be takes place in both of the members. Then we have to calculate the final stresses. So first we have to calculate the stresses in the aluminum bar and also stresses in the steel bar. So we got the value is in the aluminum bar 105 compressive stresses. So that's why here I taken the 105, which means 105 compressive stresses due to the temperature change. That's why minus 105. Here also the nature of the stresses by application of the compressive load, that is the 15.4. So here that is a compression, that's why I taken the minus. So here minus 105 minus 15.4, that is equal to the minus 120.4, which is nothing but 120.4 Newton per mm square compressive stresses. Similarly, stresses in steel, which is equal to the stresses due to the temperature rise, that is the 42 tensile stresses. That's why I taken the plus here. And also due to the applying load, so that is the value is 43.9 compression. So compression I taken the minus. So 42 minus of 43.9. So which is equal to the minus 1.9, which is nothing but 1.9 Newton per mm square compression. So this is the solution, and thank you.